Hello guys. So in this video we are going to implement the Harris code in Matlab. So I hope you have seen my video on feature detector, Harris detector. So this video. So in case if you have not seen this video, you can click on this link over here to see the video. So there I have explained in detail as to how the Harris detector works. So let us just see the algorithm. So in the last slide of that video we saw the algorithm, so we are just going to implement this algorithm in Matlab. So let us see how we can do that. So the first step is you have to compute the x and y derivatives of the image. So let us see how we can do that. So here I am reading the image over here. So this we are reading the image, taking the size. If it is grayscale, so we convert it to if it is color image, so we convert it to grayscale. So that logic is over here. So it just takes the size and sees it the shape of the size. I mean the size of the size itself. If it is 3, that means it is a RGB sort of image, so that is color. So if it is that case, then only convert it to gray, or else it is actually the gray image, right? So now these particular things over here that are used, n is equal to 3, and then taking the ceiling value. So these things are used for convolution of a filter. So these things I've explained in detail in my video of spatial filtering in time domain. So if in case you have not seen that video and you want to know how the convolution is done, so you can click this video over here. So you will understand in detail how we can do convolution in Matlab. So that is about that. So because here I have not used any Matlab functions, all the functions are all the things are done by me. So that is why, if in case you want, or else you can also use the convolve function of Matlab, 2D convolve function, so that also you can use. But here I have used my own uh, function so that I can be more specific as to how things are happening. So that is about that. Next, what I'm doing over here is basically a edge detection. Oh yes, also I have posted a video on edge detection with Matlab. So that will also give you a good insight as to how we can detect edges. So that is link over here. So that also you can see. So here what am I going to do is I am going to detect the ix and iy of the image. So that is what we have seen over here. We have to compute the x and y derivatives of the image. So that is what I am going to do here. So this I am computing using the pivot mask. So the pivot mask is over here. So these variables are just from that spatial domain thing. So I have not changed them. So HPF basically over here means it is an X filter. Sorry, this is a Y filter, and LPF means this is a X filter. I just forgot to change the names. That's it. So now this particular loop will give you the IX of the image, IX that is the X of the image, and this filter will give you IY of the image, the Y derivative of the image. So what I'll say is, let us run the loop till here, and let us see what are the IX and IY outputs till here. So in order to do that, you can just put a point over here, so that will create a breakpoint over here. So whenever you run this program now, it will run till this breakpoint. So you can see that the program has run till here. This arrow tells you that it has run till here. So now let us im show x, ix and iy and see how does it look. So in the command window, I am writing im show, oh, and so ix, iy are both double. So I need to first convert it to uint8. So uint8 and double are very important data types in image processing. So if in case you don't know why am I doing this, you can click on this video over here. I have given a detailed explanation on what is uint8 and double. So let us see how does ix look like. Oh sorry, I did this capital, so it needed small. Yeah. So this is what ix will give. Oh, I did not show you the original image. So let me first show you the original image. So the original image is in A. Okay, now if I do this, it will overlap. So first I'll need to make a figure window. Oh, figure window. So this will create a new window, and then now let me do IM show. Right, so this is the original image, an ideal image, a chessboard image. So that is what I've taken, and this is the IX. So you can see derivative in this direction. So you can see a change over here, a change over here. So those changes are recorded over here. So that is the IX derivative that we have computed. Similarly, I can show you the IY derivative. So this is the IY derivative. Yes. So similarly in the y direction the derivative, so that is the IY derivative. So yes, so we have computed over here. So let's see what is our next step in the algorithm. So what I'll do is, let me do this side by side. Yes, this is better. Okay, so yes, this is nice. So now let us see. So we have done this step. First step is complete. We have computed Ix and Iy. Now what we have to do is we have to multiply Ix, take Ix2, multiply Iy, get Iy2 and get Ixiy. So that is what I have done over here. So remember in Matlab, this dot multiplication does element by element wise multiplication. So that is what we want. We want element by element wise multiplication. If suppose there wasn't this dot, then it will do matrix multiplication. So that is the rows of one matrix into the columns of the other. So that is not what we want over here. We want element by element. So that is done over here. So now if you want to suppose run only this line, you press step. So that will only run this line and go to the next line and stop. This is a way to debug in Matlab, a very nice debugging strategy. If in case you have some errors, you can debug it like this. So we can just compute Ix and Iy over here and we get Ix, Iy. Now what I'm doing is, while doing convolution, we always see that the image size changes. So here you can see the original image was this dimension, but you can see Ix has changed. It has become 705 and this. So this is because the filter, the convolution properties basically, and I've not done any padding. So because of that also. So hence I am again recording the size in a B1 variable because I'm going to further do some steps over here. So I'm recording those. I'm recording the new size in B1. So now here the next step is to compute the sums of products of derivative at each pixel. So remember, next step is to take a window. So yeah, so suppose we see over here. So our step is, so after we have taken the Ix and Iy derivative, we have this window and we have to sum all the pixels in this window. So that is what we are doing. So that is the loop that I'm going to carry out over here. So these things, these loops are just going to do the sum of that in a window. So for that I'll first have to define a window. So what is the size of the window? So this is variable over here. You can change the size and the window will change. So for now I've kept it as 5. So this is like 5 cross 5 pixels. So there will be a 25 pixels window that we have. And this is the same logic. You take half and all this is because of this convolution. So you want to basically drag this window. So what you want is first the window should be over here, then it should shift. So this particular strategy of shifting this window is for that you need to do these all things. So next you need the value of kh because that is our Harris algorithm. So you find a threshold and you need you basically compute this particular thing. So you need the value of k. So that is normally taken as 0.4 to 0.6 something. So that here I have taken 0.04, and there is this threshold that you have to decide. So that threshold tells you whether which particular thing you want. So do you want edges, do you want corners, or do you want flat region? So mostly the algorithm is for corners, but you can also extract edges in some cases. So that is this threshold for this threshold t. And these are just pre-allocation. I'm going to use these variables down over here. So I've just made a matrix of all zeros. So this will give me a matrix of all zeros, and that I'm going to use over here. So that is all. So that's the initialization kind of a thing. And now this is the loop. So this loop basically will move the window, as I had mentioned before. Yeah, so this particular loop will just move the window from here step by step, and do something that I am written over here. So what it will do is, it will, so say for one case the window is over here at the first thing. So what it'll do is, it has kept the window over here. Now in ix2, ix2c, what will happen is, so because it is ix, so let me play with ix. So this is the ix image. It'll keep the window over here, add all the take all these pixels. So there is, so since my window size was 5, so here you can see my window size is 5, so I'll give 5 by 5 window, so that is 25 pixels window. So all those 25 pixels I'm putting it in a vector. So this ix2c is a vector having 25 pixels. Next, the same thing, 25 pixels of this particular, when the window is placed over here. Next, when the for loop changes, the window will go over in the next location, take these 25 pixels, then next location, take these 25 pixels, and the story. So all those 25 pixels are stored in ix2c for the image ix. Oh no, for not the image ix, but for the image ixx, because the algorithm is such that you have to do that for these particular things, ix squared, ix iy squared, and these things. So that is for ix2, iy2, and ixy. So ix2, iy2, ixy. Next, you compute this matrix, this H matrix. So after that, you have taken the sum over the window. So after that, you have found out these particular things. You have taken the sum over here. You compute this H matrix. So this H matrix is precisely over here. The same thing, you just take the sum. So these were a vector. These ix, iy are vectors. So those I have just taken the sum. So this becomes this x, sx2, and the story over here. Next, I just take a threshold r of this particular thing. So first I'm making this r, computing the response r. So that is determinant of h minus this k h kind of a thing. That is my threshold. So kh, that is k over here. So I could not use k over here because I was using k over here for the loop. So because of that, I used a different variable, that is kh over here. And now you just take a threshold. So here I have taken the threshold to be 10,000. So if r of I comma j is greater than 10,000, then you put it in a corner kind of output. So this is a new matrix corner that I'm going to make. So that was what I've initialized over here as zeros. So if the threshold is greater, if r is greater than 10,000, put it in corner. Else if it is less than some minus thing, minus half of the threshold, then put it into the edge kind of a matrix, edge output. And else if there is nothing of this sort, then it is flat. So this is precisely what I'm doing to imitate this particular thing, to get corners, edges, and the flat regions. So that is what I'm doing over here. So now let us just run the total code and see the output. So so I'm over here at this point of a time. If you want to run the whole code, you just press continue. So since there are so much calculations, it is taking a little time, and this time also depends on the size of the image. So my image size over here is 707 cross 1000, quite a big image. Yeah. So yeah, so you can see the outputs over here. Let us see it one by one. Okay, okay, okay. Yes, so I did not tell about this particular thing. So one thing, so there is this particular function, a very beautiful function, image SC. So I had my R matrix. So my R matrix actually has the all the values of this determinant and trace. So in if suppose you want to visualize how does this R matrix look like, you can use the image SC function. So what the image SC function does is, I can explain you with the help that so Matlab is a very nice help kind of a thing where you can understand each of the functions. So what does image SC do basically is, if suppose you have a matrix like this 0 2 4 6, like this kind of a matrix, so it takes the minimum value. So your the minimum value in the matrix is 0, and it assigns this particular color. So this is the 0 color of image SC, and the maximum value, so this is 22 is the maximum value, it assigns this yellow color. So the minimum number in the matrix will given this color and maximum this color, and then there will be the range like this. So in this way you can visualize minimum maximum things very nicely. So that is what I've done over here. So since R actually is not an image, R is just giving you a very high value for corner. So that is what you can see over here. So R is giving you a very high value for all the corners, or I guess this is better. So for corner we can see that R has a very large value for corner, negative value for an edge, and small value for flat region. So that is basically what we can use to visualize that thing. So hence I have plotted this R. So you can see that these corners are so very high that only that those are seen and others are almost zero. So that is, you can visualize this nicely over here. So for this ideal image, this does not make a lot of sense, but for others it actually it is a good thing. Now you can see this is my corner image. So you can see how beautifully it has detected all the corners. So let me put the original image. So this is the original image. So you can see how beautifully it has found out all the corners of the image. Next you can see the edge image. So this is the edge image. So here you can only see the edges, and you can see it has not taken the corners, it has only the edges, that's it. So that is the edge image. And the last is the flat image. So now this is kind of only flat region is white, that is high, and other all regions are black. So this is the implementation of the Harris code. So now here this threshold value is very important. So if this threshold is something that you will have to define. If suppose I do some change, so now let us play with this code a little bit. Now suppose that I am taking a transformed image. So now what is this transformed image is this image is basically a rotated version of this image, so 45-degree rotated version of this image. So let us play this on this particular algorithm, on this particular image, I'm sorry. So let us see what happens when I do that. So this is taking a lot of time because this image is a little bigger. So because this, so more the bigger the image you take, the more time the algorithm will take. Also this is also taking a lot of time because I have used all of my functions. I mean, I have written everything myself. I've not used any Matlab functions. So the Matlab functions are quite optimized, and they take less time. So that is also the reason. But when you write the code yourself, you use the small things that you know, so you understand better. So in order to understand better, it is better that you try to use MATLAB function as minimum as possible. So that is a good thing that you can do. Yes, so we have our output. So here in this particular output, you can see that not all corners are selected. So you can see that there are some edges also. So this is the corner image. So here you will see the importance of this image SC. So in this image SC, you can see that there are some kind of an edges which are giving a relatively high output. So here you can see that still the corners have the highest output, but there are some edges which are also giving relatively high output. So if you just see this image, you will see that, oh, there are the corners over here also, which is not true actually. It is a relative kind of a thing. So here R value for corners will be the highest, for the edge will be little low, and or negative basically, and for flat it will be low, very low. So this is the problem that we face in Harris, that you need to know what is the threshold. So you can do something else also. So that is, if suppose you, so how you will have to take this threshold by trial and error. You'll have to change the values of t, and keep on checking, keep on running the code. So instead of that, what you can do is, so the mostly the code is the same. The only difference is over here. So this was when I already knew the threshold. So now I already know the threshold, and I'm putting its value and running the code. So now instead of that, what we can do is, you first run the code and get the R matrix. So here I am getting the R matrix. Till now I have not defined the threshold. So this is actually not of any use. So till here what am I doing is, I am just getting my R matrix. That is what I want. After that, what I'll do is, I will say take a n value. So what is this n? I'll tell you in a bit. So the intuition is basically, I just want top, what we say, I just want top 2200 values. That is what I want. So according, I now my threshold is like, I just want top to 2200 values. So for that, what we can do is, I have this R matrix. You can just flat that R matrix by using this particular thing. So what will happen is, this is a matrix over here. When you, R is a matrix over here, when you do this kind of a thing, this particular format, you get R1, which is a vector. So the row or the columns of R are all concatenated to, in one vector. So if R would be a 5 cross 5 matrix, then R1 would be a 25, what we say, 25 elements vector. So that is what I've done. And next I've sorted R in descending order. And after that, you tell me which value you want to take the error. So here I have taken threshold. So here I have taken the 2200th value as my threshold over here. And after that, you play the threshold loop. So by this, what will happen is, you will only get the top 2200 values in your output. So let us see what is the corner response when you do this kind of a technique. So this might take a little more time. The reason for that is, now you have another loop that you are giving extra to the program. So this might take a little more long, little more, what is happening to me today, a little more time than the previous case. So but then this gives you the freedom of deciding a good kind of a threshold. So that is the change that you have. So on which image am I running this? So this is on the transformed image. Okay. So the transformed image, you saw that it was the 45-degree rotated image. So on that image now I'm running this particular code, and let us see what output, what does it give the output. Also here I gave this n as 2200. So this was also by doing a little bit trial and error, but these trial and errors will be less as compared to those. So that is the difference. That's all. So let us see what happens when you rotate the image and put the Harris code on it. So that is what we are going to see now. I'm purposely not forwarding the video so that you can also understand the time that is taken in both the cases. Yes, so we have got our output over here. So now you can see by this kind of a threshold, you can get a quite nice kind of a image. Nice corners are detected over here, and this also reminds me of the fact that you can see that also after rotating the particular image, Harris gives you the proper corners. So this is one of the most important properties of Harris, that it is rotation invariant. So if in case you rotate the image, so that will not affect the corner points. It will not happen that if you rotate the image, then the corner points will not get detected or something else. So that is one of the most beautiful features of Harris, that it is rotation invariant. Also it is affine invariant. So if in case now I choose a affine transform thing, so this is my affine image. So I've done a affine transform over the original image, and let us see, can it detect the corners still. So after doing an affine transform on the original image, can it detect the corners with a good accuracy is what we are looking at. Also, it is seen that the edges and the flattened things are not quite nicely detected in every case. So that will again depend on this threshold, what threshold you take. So whatever threshold you take, it will act accordingly. So for now, I have commented these particular things, but you can always uncomment and find out for yourself how does the code work for them. So I'm going to put this code in the description below, so you can take the code from there. Yes, so we have our output over here. So yes, so you can see that this is the, okay, it did not show the original image. Let me again tell him to show the original image. Oh, I will have to make it on a new window. So let me make a new window, original image. Yes, so this is the original image. You can see that I've done an affine transform, and this is looking like this now. So you can see after doing an affine transform also, it is quite nicely able to detect the corner points. There are little errors, or what we say, little noise that we can see over here, but that also can be adjusted with the threshold. But you can see over here, I guess some points are not detected. Okay, so here you can see that this is the actual image. So here this particular point over here is not detected. So affine what we say, the this particular Harris algorithm is quite okayish invariant to affine transform. Like it does its best to tell you the features, but then there are some places where it can make errors. So that is what we can see, that it is not very exactly giving you the output, but it is quite robust to affine invariance also. So we'll discuss this in my properties to Harris in my upcoming videos basically. So this is what we are going to discuss, and that's all for this video. Thank you so much for watching. Thank you.